Hey everybody. So today I'm going to be talking to you about a specific model called DiffRhythm. And if you haven't heard of it, it's the very first open sourced music generation model. And it utilizes diffusion, and I'll get into the full architecture of this model in this video. And that's kind of what this video will be about, is explaining this architecture, how it works, the inner workings of DiffRhythm overall, and kind of just to give you an overview on those lines. I have picked apart this model and dissected every single part of it. The authors, they have a GitHub repo for it, but within their GitHub repo, they say that their Colab is coming soon, and so they didn't have it. And I figured I would do them a favor and build it up. But I can 100% see why it's coming soon. I spent like 3 hours on this Colab notebook trying to get it up and running in Colab. I couldn't do it. I know 1,000,000% what issue the authors are running into with it, getting it into Colab. And then so that's kind of what I want to talk about within this overall, right? So the first thing that I want to talk about is like what actually makes up this DiffRhythm, right? So you go to their GitHub repo, and they have a good map here of a model of like in this instance a variable autoencoder diffusion model looks like. And then this is essentially like the full structure, right? It uses individual parts. We have here an LSTM, which is long short-term memory, and then we have our diffusion layer all throughout, and then we have our variable autoencoder or variable autodecoder, and then so and it goes through and it's going through if these boxes are transformer layers, and then so I'm going to explain all of this out, right? If this diagram is looking like not making sense to you, and what I just said didn't click immediately, that's the point of this video. So within this, the first thing that I want to talk about on a high level within this is that this is 100% a wrapper, right? If you depending on what your definition is, and then so I think I'm waiting for someone to and for and on social media, because that seems to be like the thing to do now, right? To pick apart this model, and then they're going to be like, oh, it's a wrapper, right? And it's going to be make a lot of news. The wrap that what it's wrapped around is very simple, right? So there's this Muck. I hadn't heard of it before, but so Muck is self-supervised music representation learning with mel residual vector quantization, and this looks like it came out about 2-3 months ago, and it's put out by Alibaba, and then so they developed Muck for music SSL. Muck applies their proposed quantitative targets and achieves state-of-the-art performance. So it's a zero-shot music encode. Like this is the music engine inside of it, right? And then from there you need diffusion transformers essentially. So it's this. This is like the engine inside, and then you need diffusion and transformers. And then so where they're getting those other two components is from a llama model, and then so. And not just not from a llama model, but from the llama autoencoder and decoder. That's the transformer architecture that they're using within this, and then so I think that's why they're running into problems. So if you run this in Colab, so what I did is I went to their GitHub repo, and then so they have the demo here, right? And if you don't know, so you can go to files. I just went to the app.py, right? And I took their model. I was like, okay, here's the model, and then they have it working in Gradio. So it's 100%. You could work it and test it in Hugging Face, right? Because they have it up here. And then when I went here, they didn't have this. So they have now their inference set up, but you can see this readme was updated yesterday, and then so when I was playing around with this yesterday, this did not exist. None of this was here. So I was just going off of pure, I'm gonna straight up reverse engineer it. So I took all of their Gradio stuff, and then I ripped out the Gradio because it doesn't work in Colab, and then I'm not trying to run any of this locally because I don't know what it is honestly overall, and then so I am running it and setting it all up in Colab, and then I spent maybe 3 hours, right? And it's I know the heck that they have run into with this. It's not going to work in its current form as a Colab demo. If they get it up in Colab, like I will be shocked. Like, because the problem is it runs into like library hell, right? Where you have like library dependencies. So you have for like the Llama transformer, it requires like Llama like a Python 3.10, and then for that muck that they have, it requires above like Python 3.11 or higher. And then so that like it's those are the two main ones, right? It's like there's stuff within the transformer autoencoder that they're utilizing that requires Python 3.10 or less, and there's stuff within that muck that I showed that requires Python 3.11 or higher. And then so when you downgrade the environment to Python 3.10, it just throws like all these errors, right? And there's like, I mean, I spent like again like 3 hours on it. So I'll link the Colab notebook here, like what I did, right? And my work on it. And the other thing is too is like I know I'm not downloading the right files too. So what will happen is I can get it to process, and then it says it asks me to upload these files, this CFM .ckpt CFM underscore full, and then the VAE. I can't find those exact files on their GitHub, like in here, like there's the like variations of these files. See, there's the Python version of these files. So that's what I have, right? Like the CFM, the DIT. I just took the Python versions from their GitHub here, right? Because that's all they have. And so I don't know if those files will work as well. And then just pointing out, that's where I get them from. So if you do happen to play around with this, and then you run into this, like where it's like asking you for those 3 files, go to their GitHub, this DiffRhythm GitHub. And then I went to model, and they're all here, but they're all the Python version. And then it's asking for the not Python version. It's asking for the .ckpt version. It's not in their repo, so like I don't know what to do about that. I couldn't get it to get past errors before this process anyway, so I'm not 100% sure it will error on this, but I'm just pointing that out. If someone does pick this up and play around with it to that step, right? But so let's go back to this, right? And this is what I want to spend a lot of time talking about, is this architecture. And then so again, like off the top, this is if you want to term it as a wrapper model, this is a wrapper. Like 1,000,000%, this is a wrapper. It's again muck plus like the Llama autoencoder and decoder are the two big ones. But within that, the very first thing that I would point out and highlight is like I don't see any companies playing around with this particular with wrappers like this in the United States. Like I see them all very focused on LLM model wrappers, which none of this is, right? So first of all, this is a very complicated wrapper, as I've kind of illustrated up to this point, right? It's you're fusing together a bunch of mathematical concepts, like huge mathematical concepts. And I think that's the best way to break this down for you further, right? Because this is like this chart is simplifying the math behind each one of these components flat out, right? So if we start with that LSTM model, this is what happens within the LSTM model, right? And this is a diagram of that long short-term memory model and module and what is going on there. So within a LSTM model and module, what it is it's a full-on, if you're familiar with an RNN, a recurrent neural network, that's what a LSTM is. It's a variation of an RNN, right? So this is in and of itself a full enclosed neural network. So this is model number 1, right? Fully enclosed. And then here's all of the math behind it. And then very straightforward, right? And then I'm just assuming that they built this out because it's like building out an LSTM model it's just math. So it's just this. So they have some libraries that they're built out there. So again, like it's wrappers, right? Like if you like, depending on how you want to label it, it's either a wrapper because they're utilizing libraries or they're building it out itself. And you could qualify and boil it down either way. So first step, LSTM, which is this here, which is a bunch of math inside of it when you break it down. And then from the LSTM layer, it goes to the diffusion layer, right? And then so this is the diffusion layer overall, which this is a variational autoencoder diffusion model. So VAE diffusion. And then in this instance, it is reliant on transformers models. And then this is going on inside of a transformer unit, right? So where you have the encoder, and then the encoder shrinks and compresses information into low dimensional representational space. And it creates a copy of the original. I can't state that these processes enough, right? When I talk about like weird things that the model does with data, that they don't rely on actual data, that they're not like your data is more of an abstract to them. It's because of stuff like this, right? When you actually look at what these models are actually doing, they're abstracting your data. They're taking it, and then your data is an image in this instance, right? And then the very first thing that they do is they compress it into low dimensional space. So they shrink it into 2D, which changes the image entirely. It changes the shape of the image entirely, but that's what they want. Right? They don't want your image. They want a 2D abstraction of your image. And then from there, they want to compress it even more. They want to take more information out of it. And then from there, they say, okay, so you give them a very sparse representation of the image, right? Like here's the shrunken, compressed abstract of the original image, and then it's like, oh, that's a panda. And then let me decode a panda for you, and then that's how the diffusion process works. And that's, I mean, literally what is going on within it, right? And this is a 300-year-old process overall. Like that's what I don't think, like, people don't understand. Like people are like so enamored by this process. Like this is 300-year-old technology. Like it's 300-year-old technology slapped on top of we'll call it 10-year-old technology with transformers, which is built on top of 70-year-old technology of perceptrons. So you have 300-year-old technology built on top of 70-year-old technology, built on top of 10-year-old technology, is really what you're looking at within this, right? But then it's just, I mean, like the market is just so enamored with all of this as being new, but just highlighting that, right? But so the thing I want to point out, and the next step I want to point out within this is, so you have the LSTM layer, which is that initial layer, and then all of this math, which gets passed over to the diffusion layer and the diffusion model, which is here. But as I mentioned, this diffusion layer and diffusion model lives inside of the transformer layer, right? So then we have to go and look at that. And so this is what we're actually looking like and actually talking about. So see this DIT block? That, like this DIT block, this is inside of one element of the DIT block. And then within the DIT block, within the DIT block, you have more around this diffusion layer, right? You have the multi-head attention mechanisms, you have softmax, like everything that goes into a typical transformer model and transformer architecture is this, right? When I say overall that transformers is over-engineered, I mean, this is what, like, so this is a transformer architecture compared to a diffusion architecture compared to the LSTM gate, right? Two of these are pretty simplistic overall as far as the actual diagram, and then it gets into very complex and advanced math, and then here you go into transformers, which like is literally just shoving a bunch of these things inside of it, right? Yeah, like how much more complex can you get overall than that? Like I can't stress that enough, right? And then so within that and that equation, it makes this whole complexity of this system what it is overall. With that, this is a pretty in-depth explanation of what is going on actually inside of this model, and then giving you kind of the architecture of the model. So again, it's starting off with that LSTM gate, that LSTM layer. Everything that you're seeing from those errors forward is part of the transformer process, and then built around the transformers. And then within that, you have the diffusion layer, where you have your variational autoencoder based diffusion, and then so that's all of that top layer is for the diffusion, which goes into the and couples with the transformer layer, and then gets you and then is built on top of the muck diffusion that Alibaba put out, and then that gives you the full model and the full architecture that you're looking at here. And then so kind of like the bottom line and the last thing to highlight within this is you can call them wrappers or you can call them like actual apps, but like it seems to me that like within the United States, like we're looking at these things improperly, right? There's very few people that like are paying attention to the actual like architectural side of these things and understanding these things, and within that then so there's less sharing overall, right? And then pinpointing again, like they're utilizing within this model like. Half of this model is llama, and then the other half is muck. So like it's a blend of United States parts and Chinese parts in this particular instance, and then without discrimination on that, it's just what works and what they're putting together, right? And then the understanding and the knowledge of how to put this together is far more important than the actual individual components. Like the reason why you're seeing just so many of these models being thrown out and able to do this is there's an advantage on this front that people don't realize. Like people are so enamored with transformers and trying to understand how they work. Again, there's a big reason why I try to stay and focus on AI architectures as a whole, right? There's far more architectures than transformers, and if you get stuck in that like transformers is everything loop, you're gonna get left behind. Is kind of what that is shaking out as. So here it is overall. I'll leave a link to the DiffRhythm fail Colab notebook if you want to look through that. I'll also link directly to the DiffRhythm GitHub, because then from there they have everything for the model. It's free on Hugging Face to play around with it right now. And it's pretty cool to check out the app, and then you can do it's like the testing the audio on it. It's I mean to me like every diffusion model has a bit of like it's run through a tin. That's just an artifact of diffusion, and this definitely has that a little bit. But it's I mean like it's good, like it's good, and it's free. And then so if you like this type of content, please like and subscribe. Thank you very much.